Thank you. Well, thank you for having me here. So I am, yes, so let's switch the gear a little bit from the more realistic physics side to the more mathematical side. So I'm going to talk about the some classification results on the unitary dynamics. So it may not be too obvious what the problem is. So let me start by defining the problem for you. So the main object that I'm interested in this talk is the automorphisms of local operator algebra. Maybe it's too mathematical term, but we know what this operator algebra is. It's just you have some lattice system and you have some spin degrees of freedom, finite on its local site. And we consider local operators acting on those spin system. That's, well, some of Hermitian local operators is what we call Hamiltonian. Automorphism is a mathematical notion that that maps from itself to itself, from algebra to itself, in such a way that it preserves all the multiplication and addition rules. It is the same. You can think of this as a group automorphisms too, the same thing. One most important probably example is the Hamiltonian evolution. If you have a Hamiltonian evolution operator here, it is a unitary. In the Heisenberg picture, it will conjugate any observable to make it another observable. And this conjugation is an example of automorphism. Actually, this is the example. There's no more automorphism than this. Then what's the question about this automorphisms of local operator algebra? I want to consider all of them in one shot, not a single of them. I want to consider the collection of all automorphisms, but that's too big a set. That's too large to consider. So I want to mod out by something, treating something trivial. But what can be a trivial thing? In this problem formulation, I just want to think about so that's too big a set. So I'm going to mod out by by those that are generated by some Hamiltonian time, possibly time dependent. This is a time ordering operator, and this is time ordered exponential. So this piece is what we are familiar with. This is the usual Hamiltonian evolution where the Hamiltonian generates. This is a unitary. And I am modding out, I'm treating all of them as a trivial one. What else can there be? You may wonder what that is. And there are many variants of this problem. Let me just, I'll get to many examples later, but let's get to the question, very precise. And in physics, we don't necessarily consider only a strictly local operator. Your operator may act on a single spin, but it may act on a lot of spins at the same time, except that, except for a given point in your lattice system, your operator may act very weakly at a far apart site. In mathematically speaking, we consider quasi-local operator, say operator O, and it has a decomposition of this form. It will be given by a sum of strictly local operators, but in such a way that the norm of the strength of the operator is decaying as a function of, say, the size of the support in an exponential way. This is also called a local operator, or technically quasi-local. You can consider a variance of this question. You can consider all the automorphisms of your operator algebra, but you do not allow any tail, quote unquote, because I'm not going to define precisely what the tail is. But what I mean is this following: if you have an automorphism alpha on your operator algebra, then I demand that whatever strictly local operator you have, the image of under that automorphism must be also strictly local. for all.
Jeongwan, a quick clarification question.
Yes.
So when you mod out this time-ordered unitary, do you allow for, are you assuming finite time evolution?
Oh, yes. Strictly finite time. Yes.
So then
Because otherwise it'll be everything, right?
Yes, thank you.
Yes. Thanks for the question. Important point. When I say automorphism, I need a locality notion of locality. So if you started with some quasi-local operator, then the image must be also quasi-local. And this is the most general setting. The no-tail category, I'm considering this, I just chop off all the slowly decaying part, and I demand that my automorphism must map a local operator to a strictly local operator. This is a subcategory. And one example in that category would be quantum circuit, which you may have heard about, but let me just repeat. Quantum circuit is a unitary consisting of small things. So, for example, I am drawing say one-dimensional spin chain here. And by a small local unitary, I mean literally a unitary supported on, say, nearest neighbor to site. There could be many layers of it. Like here, I'm drawing one layer, and the two-layer quantum circuit will look like this. The jargon circuit comes from the fact that it has been studied in the quantum computing community, and this looks like a logic circuit in the computer science, and that terminology is now carried over to more mathematical condensed matter literature these days. So this quantum circuit, when conjugating a local operator at a site, by conjugation, I can draw diagram things like this is the exact copy of the upper line, and my complex it would look like this. And the operator multiplication order is going to be my time direction. And by unitary, anything that lies beyond the light cone of my local operator will precisely cancel off. They go away, and they go away. And what you're left with is going to be some operator whose support is slightly enlarged, but not too much. And it fulfills my demand on the strict locality preserving property. Even smaller class can be considered. And this category is motivated from quantum information literature, and I call it Clifford category. So here, let's consider a strictly spin system. There will be a d-dimensional spin system, and there will be a lot. And I chose sometimes it's called Weyl operator, sometimes called generalized Pauli operator, but name is not that important. But what I mean is the following. This is the clock shift operator, and I denote it by X. And this is and Z is going to be the diagonal operator whose entries are e to the 2 pi I over D, 2 pi I 2 over D, e to the 2 pi I D minus 1 over D. So both are D by D matrices. And I call them, and you can write down a variety of operators using these operators, using this matrix and tensor products of them. And in the Clifford category, that the requirement is that your automorphism must map each X into some tensor product of X and Z on the various sites. That's my requirement, and the same should hold for this particular type. This is a much smaller category than we initially considered. I initially started with the completely general, but just locality preserving. Then I restricted to the strict locality preserving. Now I even demand that my operator shape for this particular my image for this particular elements in the domain must be very restricted. It must be a tensor product of those operator. In particular, the image of this operator must be non-entangling. It should not create any entanglement. Although alpha itself may, but this operator, the image, cannot. And the thing I am going to make trivial is going to be Clifford Circuit, of course. By Clifford Circuit is you just combine these two properties. It's a quantum circuit, but it has to be of Clifford type. So in the Clifford circuit category, with that green thing has to be Clifford too. This is what is modded out. Okay, so I am going to make a table of this. So I consider all automorphisms of Clifford type, and I'm going to mod out by any Clifford circuit that corresponds to finite time evolution, which translates in the circuit picture to be the depth of the quantum circuit is independent of system size. So why do I do that? Why should I care? Who should care about it? There is an intimate connection to the locate topological phases. So let's slightly step back and look at the context a little bit. So in the locate literature, what is studied is you consider a Hamiltonian parameterized by some time parameter, is a time-dependent Hamiltonian, in such a way that Hamiltonian obeys certain periodicity of capital T for all T. And then you consider the unitary operator generated by this Hamiltonian according to the Schrödinger equation. This unitary is not periodic, not necessarily periodic, but if I consider the one period time, then you can think of this as you can consider this some Hamiltonian by taking the log of this unitary operator. Although this is often called Hamiltonian, this it doesn't have to have any physical meaning. In particular, this Hamiltonian doesn't have to be a local operator. And over the last few years, it has been realized that not only this locate Hamiltonian that encodes the one period evolution, but actually the whole path where T ranges from 0 to 1 period, the whole path of unitary is important. And the striking thing is that if you demand that the one period unitary is actually identity, there still can be some interesting going on in this unitary. What's interesting is that if you consider say d-dimensional system, D is my space, d-dimensional system, and then you consider this unitary operator acting here, something non-trivial is happening induced at the boundary, especially if the system has a boundary. So let me just repeat. Even if my one period evolution ends up being identity in the bulk, if it is identity, even if it is identity in the closed system, in the system without boundary, it may induce something non-trivial at the boundary. That has been observed. And since this is anyway a locally generated unitary operator, anything that is induced at the boundary must respect that locality preserving property too. And so the thing that is induced at the boundary fits into my definition. It is going to be an automorphism of local operator algebra that preserves the locality. And you can actually go the other way. So what I want to do is, given any automorphism, operator algebra, there is a one parameter family of unitary generated by some local time-dependent Hamiltonian in D plus one dimension. So the original alpha, my automorphism was living on a d-dimensional space. Now this unitary lives in a one dimension higher, in such a way that the boundary action of that one parameter family in one dimension higher. Oh, I forgot one thing. Yeah, there is a one parameter family of unitary in p plus one dimensions in such a way that one period implements identity in the bulk. So it looks boring, but the induced action on the boundary of that one parameter family is my given alpha. So that's the tight connection that I want to introduce. In the interest of time, let me go on. And the next question might be, well, I have given you the connection between the automorphisms and the Floki dynamics in one dimension higher, but I didn't tell you why am I modding out these objects by the locally generated circuits. There is one. Let me just focus on this aspect. So I said that there is if there is a one parameter family of unitary in one dimension, d plus one dimensions, then the induced action may be something trivial. I'm sorry, maybe something non-trivial. But what if this path was actually a contractible? Contractible in the sense that there is a two parameter family of locally generated unitary, such that this is implementing my given unitary if S equals 1, and it does nothing entire for all t if S equals 0. So it means that there is a smooth interpolation between my time-dependent unitary evolution in d plus 1 and identity evolution in d plus 1 dimension. The induced action on on the boundary is going to be is again locally generated. I mean, it says a Hamiltonian evolution. I think it's best for me to just give you the claims, not necessarily the proofs. So this is the reason I'm taking the locally generated unitary as trivial. In that way, by focusing on the quotient structure I have defined, and looking at the boundary, I am studying the topology of locally generated unitaries in one dimension higher. One typical example of a non-trivial action induced at the boundary of a Floki evolution in the one dimension higher is so-called shift. Think about this automorphism. It's really simple. I have a spin chain in one dimension, say, and then give me an operator x at any location. Well, I think I've used the notation O. Give me any operator that's supported on the one side, say, and then I consider an automorphism of operator algebra that whose image of O is nothing but O acting on a one side to the right. It's really a translate. Yeah, translation is a bad word. But in higher dimensions, it doesn't have to look like a translation. It can be a permutation of things, and I still want to consider that. You can't. Why is this non-trivial? Why can there be a Hamiltonian whose unitary whose solution by the Schrödinger equation is my shift? Can there be such a Hamiltonian? The answer is actually no. Here's a very simple example based on your exposure to the topological literature. Consider consider a quadratic Hamiltonian, in fermions. Say, I'm sorry. Each side is a complex fermion, so it is now described by two Majorana modes. Say A and B. As this is side J. And the one Hamiltonian can be written as I times AI BI. These are Majoranas. And the other Hamiltonian is AI plus 1 BI. Yeah, this I is different. So this Hamiltonian and that Hamiltonian, they only differ by the location of A here. So if I had a translation operator that acts on the, say, A mode, and I act by shifting one side to the right, then by that translation, H naught, the trivial free fermion Hamiltonian, is now mapped to the Kitaev chain, H1. So if H1, if alpha was was locally generated automorphism, then using that local generator, I can make a continuous path from H0 to H1. And since this is automorphism, the spectrum doesn't change at all. In particular, the gap doesn't close. So it better that the translation is not described by Hamiltonian evolution. And this is a proof, well, based on the knowledge that the H1 is non-trivial. Now I want to talk about something else. So for a long time, this is the situation up until 2018, until among all studied flow case systems, this shift is basically the only example of non-trivially induced action from a flow case style evolution in one dimension higher. And there comes another example, and to explain the other example, I need to introduce this construction. Let's think about the famous example of toric code. Toric code consists of it's a 2 plus 1 dimensional Hamiltonian system where it's exactly solvable, and it contains anyons that are called E, M, or Spinon or Wisen, and they're composite fermion. If you have 2 copies of the toric code, then there will be another set of those anionic excitations, completely independent, has nothing to do with the first copy. But it turns out that this can be written as 2 copies of so-called free fermion. Free fermion theory is an anionic theory that consists of literally 3 fermions, say psi 1, psi 2, maybe F is better, F1, F2, F3. And since there are 2 copies, let me bring another copy denoted by G, G2, and G3. you can make a map between these two in such a way that all the algebraic data pertaining to the Annian statistics is preserved. And now this looks very different from the unitary code, and indeed different, but two copies of them, they are equal. And there is a so-called Walker-1 construction that allows you to have one copy of this three-fermion theory at the boundary. The conceptual construction goes like this. So here I have two sheets representing these two, or that two. They're the same thing. And I imagine many layers of them. And then I couple this bottom layer and the up layer, this bottom layer and up layer, and drive a topological phase transition by condensing a boson. Everywhere in the so the bulk becomes trivial. Trivial in the sense that there is no anionic topological excitation left. But the remaining piece at the top and bottom, they are never touched. So any topological excitation that leaves on the top layer and the bottom layer leaves as they are. And they happen to be one three-fermion theory at the top and another three-fermion theory at the bottom. So this construction as its own, I mean, as it stands, as I write, there's nothing special. What is special is that the end result has commuting Hamiltonian. And by commuting Hamiltonian, I mean the usual Hamiltonian, but each term, they are all commuting. In particular, it has a very boring energy spectrum. It's trivially gapped, but nonetheless, at the boundary, you can define such an interesting thing. What makes this more interesting is that the individual three-fermion theory, one copy of three-fermion theory, does not have any commuting Hamiltonian description. This is a widely believed conjecture. I don't think there is mathematical proof, but I have not seen anyone who doubts this conjecture. This is based on the fact that the three-fermion theory has a chiral edge mode, and the commuting Hamiltonian, how can commuting Hamiltonian be generated a chiral edge mode? Because the chiral edge mode should have some description in terms of commutator in the bulk. In the commuting Hamiltonian, that commutator trivially vanishes. And well, I gave you an example of this Walker-1 model as if it were explaining only this particular example of three-fermion theory at the boundary. But the machinery is much more general. Given any Annian theory, that this Walker-1 machinery generates a Hamiltonian in 3+1 dimensions. So this is 3+1. In such a way that the bulk does not have any trivial particle, so it looks very mundane. But at the boundary, it may have some chiral theory. Yet the bulk Hamiltonian remains all commuting everywhere, including the boundary terms. Now, given such a state, people have said that, oh, there is a disentangler dimensional state if I didn't expose the boundaries. Well, people have said that, but unfortunately, there isn't any explicit construction of disentangling transformation. By disentangling transformation, I mean the following. Transformation is going to be a unitary that is locality preserving. So it is a candidate object that I want to consider. It maps the ground state of my Jeongwan model into completely trivial state. Say, all spins up. In particular, it has no entanglement. And people have said something even stronger, that this U can be chosen to be locally generated. Another way of saying this is roughly the same as, well, roughly, I mean, you can make it more precise, that this topological phase represented by, the topological phase in the static Hamiltonian case, represented by this ground state of Jeongwan model is actually trivial state. There is a gapped Hamiltonian path gapped path of local Hamiltonians whose ground that connects the ground state from here to the completely disentangled state. And now let me argue that one particular type of disentangler is impossible. So here the disentangler was focusing on a single state. The only requirement was that my ground state is mapped onto a completely disentangled state. That was the only requirement. But let me demand something much stronger. What if I demand that the Hamiltonian is disentangled? It may not be a too trivial statement, but what I mean is that state in the energy spectrum, not only the ground state, every state in the energy spectrum is now mapped to that of more hands-on explanation would be that the conjugated Hamiltonian is going to be written as some terms, and each of them is actually a product of very simple single qubit, single spin operators. Well, you can consider a situation where such a thing is possible. And if you look at the all the disentangling transformation in the literature of SBTs, all the disentangler are of this form. They are not only disentangling the ground state, but they also disentangle the entire spectrum. That's not a requirement, but that was necessary because that's usually the only way you can confirm that you have disentangled your ground state. Now, okay, let me use my 5 minutes to explain that such a U, if it exists, cannot be locally generated. And then I'll so the most interesting property of the walk-around model was that there was this 3 plus 1 dimensional bulk, and that had a 2 plus 1 dimensional boundary, but that was chiral. And if my unitary was locally generated, then I should have been able to truncate my unitary in such a way that it does nothing near the boundary and completely disentangles in the bulk. If your unitary was a say Hamiltonian evolution, then keep the Hamiltonian terms here. Well, Hamiltonian, I mean, not a Hamiltonian of the usual system, but your disentangler. Keep your terms here, but zero out the terms there. So it does nothing and it does everything at that point. But since you're transforming the Hamiltonian into the trivial form, you will be able to, once you apply this transformation, then deep in the bulk, everything will become completely trivial. Near the boundary, everything is intact. So you are effectively reducing your system into a quasi 2 plus 1 dimensions. And since I'm conjugating my Hamiltonian by unitary, all the commutativity remains, and you will be able to realize your chiral theory using commuting Hamiltonian. And that doesn't sound right. So the only assumption that fails should be that U was actually locally generated. So this example is a non-trivial example in my problem. I wanted to consider all possible locality preserving automorphisms, and I try to mod out by locally generated ones. Those are given by Hamiltonian systems. And beyond the example of translation, this is yet another whole new class of example. And it turns out, now you can work on my Clifford category, and my result is that there is a periodicity in dimension. So the QCA is a synonym for, well, yeah, it's an acronym for quantum cellular automata, but that's only to make a connection with some other quantum information literature. This is the object I wanted to study. And if you model out Clifford circuits and shifts, the remaining thing is non-zero. And the disentangling transformation for that 3-fermion walk-around model sits right there. It is a different class of locally preserving unitary that goes beyond the examples that people have known before. I am already at almost finishing time. Let me skip that part. So here are some concluding remarks. There has been there is a complete study of this Floquet phase in a topological sense that implements identity in the bulk. If you are studying the Gaussian unitaries in the 3-fermion case, then the machinery of K-theory that was used to classify free fermion static Hamiltonian system just carries over, and the problem there is now solved, closed. The case of Clifford category has touches, well, it goes beyond that free fermion framework. It has nothing to do with that free fermion framework. So I may say it is something to do with interaction. This is only very schematic, but there is interesting periodicity in dimension too. It depends on the local dimension. If your fundamental degrees of freedoms are all 2 dimensions, then there is a periodicity of period 2 across dimensions. But for alt primes, the periodicity becomes 4. I did not explain anything why this happens, nor I did not why these groups appear. That's saved for some other time. But I found it interesting that, beyond that free fermion category, free fermion framework, there is another periodicity in dimension. So maybe it gives some insight into the classification of interacting topological phases. And there's a common theme in all of this business that awaits to be generalized to a more general setting. There's a dimensional reduction. So we started with the flow key dynamics in dimension D. And then at the boundary, we obtain a unitary that preserves locality, but is not necessarily locally generated. And you can characterize such a unitary by going 1 dimension lower. And I'm sorry, this is something I did not explain anything. And this dimension, well, all I wanted to say is that there's a dimensional reduction procedure that enabled me to obtain such a table. And I hope that technique is applicable to some other situations. So let me conclude with the questions I encountered during this study. The ground state of the 3 fermion Walker-1 model is claimed to be an SPT, symmetry protected topological state, which by definition is disentangleable by some quantum circuit of finite depth in the absence of symmetry. But in the literature, there is not any circuit that shows this. The argument I sketched rules out that you will be able to disentangle the full spectrum of the Hamiltonian, but there's a chance that the ground state is still disentangleable. And that's what matters when it comes to SPT study. But then what is it? Your calculation should not disentangle your Hamiltonian. It really have to be specific to your ground state. What is it? That's one concrete question. And the status of the belief that the chiral states in 2+1 dimensions is not realized by a commuting Hamiltonian is only conjectural. And I see one mathematical path to prove this conjecture, and that is to show that 1-dimensional boundary of a 2-dimensional commuting Hamiltonian is always gappable. You can introduce the space boundary, and you can introduce boundary Hamiltonian terms in such a way that everything is commuting. And can you always do that? I don't think this is known. And well, why this is interesting? Because that means that any commuting 2-dimensional commuting Hamiltonian will host some boson if it realizes an anyon theory. It is believed to be true, but there's no mathematical proof, and I ask for that. Right. Well, these 2 questions involve something that I didn't explain, so let me skip that. And I came to one concrete conjecture in the original question. So give me all automorphisms that preserve locality in 3 dimensions, and I forget about all those things that are locally generated, and I forget about the shift. Then what is left is going to be something in mathematical literature called the Witt group of modular tensor category. This is a coarse or classification of annual theory by modeling out the quantum doubles, those that are represented by Leavenworth models. And I think this has some chance of being true. Yeah. So let me stop there. So this is just a closely related but different question than the usual question of topological phase classification of static Hamiltonian systems. And I believe there's a fuller interrelations. Thanks for your listening.
Yeah, thank you very much, Jeongwan, for this provocative talk. So I was wondering, so I guess in Kitai's periodic table, the bot periodicity so emerges from applying K theory to classify vector bundles.
Yes.
Are you applying algebraic K theory to construct this table?
Well, it is closely related, and even math literature calls it K theory of quadratic forms. It's formally different. So it's like a degree 2 thing beyond degree 1 thing. Degree 1 thing is K theory of vector bundle. Degree 2 is you consider the quote unquote inner product of those vectors in your bundle, and that results in the quadratic form. Yeah, they are formally different, but yeah, one keyword that you might want to look up is the L theory, which appears in the surgery theory in topology. Yeah, there are relation, but they are not the same.
But is there any analog of this stable equivalence?
Yes. So I don't think I explained that, but all I do requires a stable equivalence. You are allowed to add in additional degrees of freedom, and then you're allowed to introduce automorphism acting on that system. And my table actually requires such a stable equivalence. And without those, the table would have been very, very much more complicated.
Okay, thank you. Okay, thank you very much, Jeongwan.
All right, thank you.
We've run out of time, so yeah, let's return here after the lunch break.